Okay, let's continue. Sorry, I was interrupted by my kid. He got in. So let's continue. So we just talk about that, starting from the steady state, starting from the integral mole balance equation, with steady state assumption and with no reaction assumption, and we will find out that actually the total flux of A um, in this region is a constant. Okay, and similarly, the total flux of B in this region is also constant. It equals to 0 because the flux of B at the water air interface, that is location Z equals L, is 0 because at equilibrium, air cannot dissolve in water, right? Because water is already saturated with air, so there's no air flux going into water. So NB at this location is 0. And because NB is 0, is a constant throughout this region, so NB is 0 everywhere, right? So that just gives us the convenience, as we will show later, to further solve this problem. Okay, so now we can start from the total mole flux equation. That is, total mole flux of A is made of the convective flux and the diffusive flux. And the convective flux is mole fraction of A multiplied by the total mole flux, right? Now, we just derived that NB is 0. That means the total flux of A is basically equal to flux of NA, flux of A, right? Sorry, the total flux of A plus B equals to the total flux of A, right? So then if we plug this back into this equation, right, which gives us this, and then if we move this XA NA term to the left, that gives us NA equals JA divided by 1 minus XA, right? So, and we know JA is a diffusive flux, which can be solved by Fick's law. And then we can just plug in the Fick's law, right? That gives us here dx over dz. And because NA is a constant, then this whole equation just becomes a ordinary differential equation about XA and with respect to Z, right? And if we can separate variables, we can solve these ordinary differential equations by hand, which is what we do here, right? If you move dz to the left and move, dxa to the right, and then move all the terms that are related to xa to the right, then we can find out we can actually integrate and solve this equation to be this. Okay, and then NA is dependent on this equation, in which here XA0 is the mole fraction of A at the mouth of the cup, mouth of the beaker, and XA is a mole fraction of A at any location Z in our control volume, right? In this case, the problem is simplified to a 1D problem in the Z direction. And from this, you can also get the mole fraction of A, XA, at any location Z, and it's basically a depends on Z exponentially. And because XA is 0, that's the mole fraction of A at the mouth of the cup is 0. If you plug in that gives us XA equals this term, right? So XA basically decays. So basically decays with respect to Z exponentially. Okay. Well, actually, yeah, exponentially. So now let's come back and look at the problem. So we have the diffusive flux of A that can be computed by, now we have XA, right? Then we can compute the diffusive flux of A based on Fick's law. Then we can have convective flux of A to be the total flux of A minus NJA, right? We have solved NA in the previous slide, and total flux of A is this, right? Similarly, here the diffusive flux of B, right? Because it's a binary mixture, JB is minus JA, right? Which can be derived if you write down the Fick's law for JB, right? Which is dXB over dZ, and XB is 1 minus XA. That's how you get JB equals minus JA. Then convective flux of B is the total flux of B minus diffusive flux of B, because the total flux of B is 0, and the diffusive flux of B is minus JA. So that just gives you the convective flux of B to be JA. And the total flux of B, which is, this minus JA plus JA, that's 0, right? Which means although the total flux of B is 0, we do have both diffusive flux of B, right? Diffusive flux of air that's going down into the beaker. But this diffusive flux of B is basically canceled by the convective flux of B, from the water air interface upward, right, by this convective flux of B, right? So now we have the diffusive flux, convective flux, and total flux. We can compute the velocity of A, right, with this equation, the molar average velocity of the mixture, in this case, and the velocity of B, which is 0, right? We find out the molar average velocity of the mixture, which is equals total flux of A plus B divided by the concentration. And because NB is 0, that gave us NA divided by C. This is non-zero. Okay. And VA is also non-zero. Okay. Further, now let's come back. Let's further drill down this and see how we can solve the question we raised initially, right? So now, because we know that at the mouth of the cup, the mole fraction of A is 0, and we know that at the water air interface that is at location Z equals ZL, the mole fraction of A equals, if you apply Henry's law, that is PAS divided by P, right? Because the interface is at equilibrium. So the mole fraction of water in the vapor phase at interface equals to the ratio of the saturation pressure of water divided by the temperature, by the pressure of the mixture. Now, if we plug in these two into the flux equation we've solved in the previous slides, you get this, right? Now, if we examine this equation, we find out, well, NA is a constant, but it's a function of L, whereas all the other parameters are constant, right? And they don't dependent on time or location, right? But here, L is NA depends on L, and L is a function of time, right? Because as water evaporates, right? So the distance between the mouth of the beaker is getting from the mouth of the beaker to the air-water interface is increasing, right? It's a function of less. Function of NA is a function of L. And then now let's go back to the original equation. We wrote down about the mole balance of water in the water phase, right? We have dNA dt equals minus NA multiplied by AC. So NA here again, it's a number of moles of water in the liquid phase. NA is the flux of water vapor leaving the water-air interface, right? AC is a cross-sectional area of the cup or the beaker. Now, we can, NA is going to be dependent on the volume of the liquid phase or the, right? We can write down that equation. So NA is the total volume of the liquid phase, which is across the sectional area of the cup or beaker, multiplied by the height of the liquid phase, which is the difference, which is the difference of the total height of this cup or beaker minus the distance of between the mouth of the beaker to the air water interface. Okay, that gives you the total volume of the liquid multiplied by density of water, that gives you the mass, total mass of water, divided by the molecular weight of water, right? That will give you the moles of water in the liquid phase, right? Now, if we plug this into this equation, we can convert dNA dt to be dL over dt, right? Because in this whole equation, everything is constant except for L. L is changing as time goes by, right? So we get this. Now we rearrange this. We have dL over dt to be this equation, to be dependent on A, right? So to solve for this equation now is equivalent, to solve for this ordinary differential equation for NA is equivalent to solve this ordinary differential equation about L, right? Because NA and L is simply related to by this equation, this algebra equation. Okay. Now we just found out NA is basically dependent on L, right? So now if you just replace NA here with this equation, right, that gives you this whole ordinary differential equation in which we are solving an ordinary differential equation about L, right, dL over dt. And all the other parameters are constant that do not dependent on T or do not dependent on L, right? And now you can separate variables, and you get dt on the left and all the dl to the right, and this whole term is constant. Then you can solve for T. The time T as this function in which L0 is the initial distance between the mouth of your beaker to the air water interface, and L is the the distance at a time T. Now, if we want to know the time required for all the water to be dry out, then we can just let L to be H, right? H is the total height of the beaker, right? So when L equals H, that means the height of the liquid water phase in the beaker is 0, right? That's when the all the water dries out, right? Then you just solve this equation, you can get the time. So there are several variations of this beaker problem we can consider. And for example, we can have different boundary condition, right? If we have a cup sitting in a humid room, right, then Xc0, right, that's the mole fraction of water vapor in the at the mouth of the beaker is not going to be 0. That will be dependent on the humidity of the room. We could have a different geometry, right? Let's see, you have a bottle of water with no cap, right, instead of a cup of water. Then the cross-sectional area of the bottle will be dependent on the height, right, on the location. And in this case, you should use the instead of the flux, you should use kind of flux multiplied by the cross-sectional area. That gives you total flux, not flux, total just NA multiplied by the area. Okay. Well, you could have another case. You could have a capped cup or a capped bottle, but there's a crack in the cap, or the cap is only is loose, so it's not tight. So in this way, there will be mass transfer happening through the crack, right? Or through the gap between your loose cap with the with your bottle, right? Now, this mass transfer through this crack is like a diffusion through a channel, right? And we have solved this problem, diffusion through a channel between two bulbs. We've solved this problem. In this case, this is going to be the limiting step, right, for the mass transfer, because the crack is going to be small, or the gap between a loose cap with your bottle is going to be small. So there's a huge mass transfer resistance. So mass transfer is the slowest step. With that assumption, you can assume equilibrium inside of the cup, right? So for this bigger problem, we just solved. There's a concentration profile in the cup, right? Which means it's not in equilibrium. But in this particular case, you can assume inside of the cup, in the vapor phase, it's in equilibrium. So the concentration of water vapor in that region between the liquid water and the mouth of your container is uniform everywhere. Okay, that's all I have today. Good luck with your exam, and hope these real life examples can help you better understand these concepts, and to help you to learn to use the concepts and the knowledge we've learned in our class to solve some real life mass transfer problems.